Hello friends, today we are going to discuss a new concept, that is the radius of gyration. In the last lecture we have discussed about the moment of inertia of a body which is rotating about some particular axis. So this is the rigid body and this rigid body is rotating about this axis. So the moment of inertia of this body of mass m. So what is the masses of the body? This body has m1, m2, m3 dot up to mn masses. Now the total mass, because this is a continuous body, so the total mass is the addition of all the masses of the body. So the moment of inertia of this body, this is 3D figure, this is 2D figure. So the moment of inertia of this body is given by I, which is the first particle into the square of the distance from the axis of rotation of that particle. So this is m1 r1 square plus the second particle m2 r2 square dot to mn rn square. In this way we find the moment of inertia of the body. Now we are going to discuss about the radius of gyration, and the symbol for the radius of gyration is K. We know a radius of gyration of any body about a given axis of rotation is the distance of the particle from the axis of rotation. So the radius of gyration of this body about this axis of rotation, first of all, it is a distance from the axis. Radius of gyration is a distance. So it will be measured in meters, or in SI system centimeters. So it is a distance of the particle, of one particle from the axis of rotation. Now one particle, so we are considering like this axis, this is the similar axis. So we are considering, instead of this whole body, we are considering only one particle. So this body, which has number of particles, it has mass m. We are considering a single particle of mass m here. Now the distance of the particle from the axis of rotation. So from this axis of rotation, the distance of this particle, which is k. This is the radius of gyration. But how and why? How is the particle? How is this particle whose mass is equal to the whole mass of that body? So the mass of this particle is equal to the mass of this whole body and kept. How is this particle kept? Such that we get the same moment of inertia as that of the original body. So the moment of inertia of this body about this axis of rotation is this. So when instead of this body we are taking one particle, a point body, but mass of the point body is m and it is at a distance from the axis of rotation k, supposing. So the moment of inertia when this body of mass m, this point mass having mass m is rotating about this axis, we are getting the same moment of inertia I. So both are same. So such distance from the axis of rotation is called as the radius of gyration. So both have, this is also equal to mk square. So the moment of inertia of both the bodies is same, and this, in such a case, this k is the radius of gyration. K we can describe as k is equal to under root of I by m, where I is the moment of inertia and m is the mass of the body. Now when the masses of the particles inside the body are to the axis of rotation, then the radius of gyration is very small. When the masses are distributed at a larger distance from the axis of rotation, the radius of gyration is large. Now, this we consider here. We are considering a ring, and the ring is rotating with angular velocity omega. This we are considering a ring
is rotating about an angular velocity omega about an axis perpendicular to its plane.
The moment of inertia of the ring, as according to what we have calculated in the last lecture, is mr square. Now, according to the radius of gyration formula, the moment of inertia, I will write it as moment of inertia of this ring IR is m into kr square, where kr is the radius of gyration of the ring. So, equating both, we get mr square is equal to m kr square. So, r square is equal to kr square. So, kr is equal to r. That is the radius of gyration of the ring, is the radius of the ring itself. Now, here we consider a disc. Now, this disc is rotating with angular velocity omega
About an axis perpendicular to its plane.
Now, according to our last lectures, the moment of inertia of disc is half of mr square. So, moment of inertia of the disc is, but according to the radius of gyration formula, the moment of inertia of the disc is m kd square.
Half of m r square.
Equating these two equations, because the left hand side is the same, we get m kd half of m r square is equal to m kd square. So kd square is equal to r square upon 2. Kd is equal to r by root 2. When the ring and the disc both are of same mass, the radius of gyration of the ring is r, and the radius of gyration of the disc is r by root 2. That is, the radius of gyration of ring is greater than radius of gyration of the disc. The mass of the ring is distributed at a distance from the axis of rotation. So, whenever the mass or the particles are distributed at a larger distance, the radius of gyration is more. When the particles are near, then the radius of gyration is less.